Hello friends, in the previous video we have seen how to write acceleration in Cartesian coordinate, and that is the instantaneous acceleration, and particularly we discuss for case of two-dimensional motion. So two-dimensional motion is a motion in which objects move along a plane. This means velocity has two components. It has Vx and Vy component. And at that point of time we have learned how to calculate acceleration of an object if it is moving in a two-dimensional plane. In terms of Cartesian coordinate, we can write acceleration something like this. So acceleration vector A is equals to x component of acceleration multiplied by the unit vector in the x direction plus y component of acceleration multiplied by the unit vector in the j direction. So this is a way by which we can represent the acceleration vector. Now in this case the first term basically denotes the component of acceleration along the x direction, and the second term denotes component of acceleration along the y direction. So this is one way in which we can represent the acceleration by breaking the total acceleration into two components, that is x direction component and y direction component. Basically there is another way to write the acceleration vector, and that is decomposing the total acceleration into two directions, but this time this direction are not Cartesian direction, x and y direction. This time direction is in the direction of velocity and in the direction of perpendicular to the velocity. So what we are saying? We are saying we can represent alternatively the acceleration vector parallel to velocity vector and perpendicular to the velocity vector. So let us try to understand all this. So let us say I have a particle and this particle is moving along this path. So this is the projectiles or this is a particle's path. This is not a case of projectile, it can be projectile also. So this is a path of particle. Now at certain point of time this particle is at point P. So this is the particle position at say t is equals to t1. Now this particle will have a velocity. So if I make a tangent at point P, I will get the direction of velocity of this particle. So this line is basically tangent to point P, and that is basically direction of velocity. So velocity is directed in this direction. So this is the direction of velocity. Now we can also choose another axis, this axis. This axis is perpendicular to direction of velocity. So we have considered two axes. One axis is in the direction of velocity, that is tangent to the path. Another is perpendicular to the direction of velocity. So we have two axes, one is along the velocity, another is perpendicular to the velocity. What is my target? My target is, can I break my total acceleration vector along these two axes? So let's say at point P, the acceleration vector for this particle is something like this. So this is total acceleration vector for this particle. Now what we have to do is, we have to break this into two components. So I will basically take this component and take this component. So this component is here, the first component, that is along the perpendicular to the velocity direction, and this is parallel to the velocity direction. So this is parallel to the velocity direction. So now I have two velocity component, basically two acceleration component. One is along the velocity direction, another is perpendicular to the velocity direction, or I can say perpendicular to the path, because the direction of path and direction of velocity and direction of tangent all are in the same direction. So this component of acceleration is basically component of total acceleration parallel to the path, or I can say component of total acceleration parallel to velocity, or in the direction of the tangent. Similarly, this component of acceleration is component of acceleration perpendicular to the path. So this is perpendicular to the path. If you know this angle theta, basically you can calculate the perpendicular component and the parallel component. In that case, perpendicular component will be a cos theta. So I can say perpendicular component will be a cos theta and the parallel component will be a sin theta. So we can calculate these two components. Now why we are basically decomposing acceleration into these two components? What is the advantage of using all this? So there is advantage, and the advantage is the parallel component of acceleration, that is parallel to the direction of velocity or tangential direction acceleration, basically gives you the change in the speed. That is important point. So this gives you change in the speed, and perpendicular component, that is in this direction, gives you change in the direction. So if you are measuring the perpendicular component, you are basically measuring the change in direction, and if you are measuring the parallel component, this means you are measuring the speed change. So these two directions are useful because they give what is the magnitude of direction change, or how the direction is changing and how the speed is changing. Parallel component, a speed change; perpendicular component, direction change. To further illustrate, let us try to take some special cases. What we can do is, so this is my total acceleration vector. So this is the total acceleration vector. This is the perpendicular component and this is the parallel component. And the particle is moving along this curved path, and particle as t is equals to t1 at point P, as I said earlier. Now what will happen if my perpendicular component is 0? In that case, I will only have parallel component of acceleration. So this component will only survive. The perpendicular component is 0 in this case. Now if you remember what I said earlier, the parallel component denotes the change in the speed of the particle. So let us try to see. At this point, at point P, velocity of this particle is v. So this is the velocity. I can show the same thing something like this. So this is the velocity. Now after certain point of time, this velocity has increased and this velocity is now v2. So this velocity has increased and this velocity is again in the same direction. This is because this component of acceleration is 0. So this means only velocity is changing, magnitude is changing, direction of velocity is not changing. So what I am saying, when the perpendicular component of acceleration is 0, this means only the direction, only the magnitude is changing, direction is not changing. This means the object is moving in a straight line. So if the object is moving in a straight line, the direction of velocity first is v1 in this direction, then v2 will also be parallel to this vector. So v1 is this vector, then v2 will also be parallel to this vector. So magnitude can increase, but the direction will remain same. So v2 has same direction as v1. Now if you calculate change in velocity, that is v2 minus v1, so this will give you change in velocity vector. Once again, the change in velocity vector is also in the straight line, and this is in the direction of v1 and this is in the direction of v2, because v1, v2, delta v all are having same direction. So this means if tangential component is only there, perpendicular acceleration component is 0, in that case I can say object is moving in a straight line, because the motion is not changing the direction. So this has only possibility when the object is moving in the straight line. In this case, you can see acceleration is what? Acceleration is simply dv divided by dt, or you can write in limiting case dv by dt. So this is acceleration. So if you divide by dt, you can get the acceleration. So direction of acceleration will be same as direction of velocity. So this is direction of change in velocity. So this is the direction of final acceleration. So you see, when the speed is changing only, in that case you will have perpendicular component of acceleration is 0, only tangential component or parallel component will exist, and in that case only a speed will be changing, particle is moving in a straight line, and there is no change in the direction of the particle. And this is here. So only in this case only a speed changes, not the direction, and acceleration in this case is parallel to the velocity. So as I said, if you have perpendicular component is 0, you have only one component that exists, that is parallel component, tangential component, and the speed is changing. So this is one advantage, that if you know that object is not changing its direction, it's only changing its speed, this means you know that the perpendicular component is 0, only a parallel component of acceleration will be there. Now the second situation we can have, what will happen in the second situation? In the first case I said the perpendicular component is 0 and the object is moving in a straight line. Now in the next situation I can say the tangential component or parallel component is 0. What will happen in that case? That is, now in the second situation when the parallel component is 0. So what will happen when the parallel component is 0? So this means now this time this component is 0. So this component does not exist. So acceleration is the total acceleration in this case is like this, but the parallel component is 0. This means only this part of acceleration exists. This means now only there is a direction change. There is no speed change, because this component of acceleration, that is tangential component of acceleration, tells you about the speed change, but there is no speed change because there is no component in this direction. So this time only acceleration will change, only the perpendicular component of acceleration will change. Now when you have such kind of situation, velocity component is constant, that is a speed is constant, magnitude of velocity is constant, a speed is not changing, only the direction is changing. When you see such kind of situation, you see such kind of situation in circular motion, when the speed is constant but the direction is changing, each point direction is changing. So you have a circular motion case where the parallel component is 0 but the perpendicular component only exists. This means only direction change exists, there is no speed change. To illustrate, let us say I have an object and this object is moving, and the velocity at certain point of time, the velocity is v1. Now since this is a case where the parallel component is 0, this means velocity is not changing. So at certain point of time the magnitude of velocity will remain same. So at certain point of time, let's say t2, magnitude of velocity will be same. This means v1 has this much of length, then v2 after some time will also have same amount of length. So this is the velocity vector v2 at time t2. What will be the only difference? The difference is the direction. Initially your velocity is along this direction, now velocity is along this direction. So direction has changed, there is only difference, and this angle by which this direction has changed is phi. Let's say this angle is phi. So we can basically make this triangle and then we can find what is delta V. So V2 minus V1, so I can write in this triangle, so V1 plus delta V is equals to V2. So what I am using? I am using simply triangle law of addition of vector. So V2 is equals to V1 plus delta V. In other words, delta V is equals to V2 minus V1. So this is the direction of delta V. Now what is acceleration? Acceleration is nothing but dV by dt. In other words, I can say direction of acceleration is same as direction of change of velocity. This means this is the direction of dV, then in the same direction parallel to this direction will be the direction of acceleration. So this is the direction of acceleration. So that is perpendicular to the path, perpendicular to the velocity vector. Now as you take this phi very small, as phi becomes smaller and smaller, this dv basically becomes perpendicular to v1 and also perpendicular to v2, because this angle is very small. If you take delta t tends to 0, in that case this angle becomes smaller and smaller, and this becomes perpendicular to this path and perpendicular to this path. This means your dv vector or acceleration vector will be perpendicular to v1 and perpendicular to v2. So your acceleration is basically perpendicular to v1 or v2 with constraint that delta t tends to 0 for a small amount of time. So this is what here I have written. For a small change of delta v, for a small change delta v is, for a small change of delta v, I can say delta v is perpendicular to v1 and this is also perpendicular to v2. In this case only direction changes, not the speed. So as I said, if your tangential component, parallel component of acceleration is 0, in that case there is no speed change, only change in direction of velocity. So there is no change in the speed. As phi goes to 0, delta v is perpendicular to velocity vector v1 and velocity vector v2. So this is obvious. So as this angle goes to 0, this vector, that is the acceleration vector, and which is same or parallel to the delta v vector, both becomes parallel to perpendicular to v1 and v2. That is 90-degree angle between v1 and delta v and v2 and delta v. So this time you see, if you have tangential component is 0, you have acceleration perpendicular to the velocity. So your total acceleration is perpendicular to velocity, because in that case what is happening? Parallel component is 0, tangential component is 0, only perpendicular component exists, and in that case I can say velocity vector and total acceleration vector is perpendicular to each other. And finally, what will happen if both components exist? This means you have the tangential component and you also have the parallel component. So you have the tangential component of acceleration that exists, that is parallel component of acceleration, and perpendicular of component of acceleration. In the previous two cases what we did? In one case this component does not exist, in another case we said this component does not exist. But now what I am saying? Now I am saying now both components are there. So this component is non-zero and this component is also non-zero. This means your total acceleration vector will be something like this. So this time your magnitude of vector, that is speed, is changing, and that is given by this term, and direction is also changing, that will be given by this term. So if you have an object that is moving in the straight line, in that case you have situation like this situation. And if you have an object that is moving in circle, in that case you have this situation. So in circle you have this situation. Now you have a situation in which these two components exist. This means it's neither in a straight line, not in a circle. It's some trajectory. It's not a straight line. It's some curve, but not circle. So in that case, you will have this situation that acceleration will exist. So total acceleration will have both component. This will have tangential component and this will have perpendicular component. Now for this general case, there are three possibilities. We will discuss different possibility. So different situations for a particle moving along a curved path. So if a particle is moving along a curved path, different situation can arise. What are these different situations? First situation, when the speed is constant along a curved path. As I said earlier, a speed is constant. This means what? The tangential component, the parallel component is 0. A speed is constant. This means the perpendicular component will only be there and tangential component is 0. So this means in this special case, this component is 0. So there is no acceleration parallel to the velocity vector. We have only acceleration that is perpendicular to the velocity vector. So I can say in this case acceleration will be inclined, or will be total acceleration will be in this direction, that is perpendicular to the direction of velocity. So when a speed is constant along a curved path, I can say acceleration is normal to the path. So this is total acceleration, and this is the path direction or tangential direction or direction of velocity. So total acceleration is perpendicular or normal to the path or to the velocity vector. Second situation can arise when a speed is increasing along the curved path. So this means the speed is increasing. So this means you will have tangential component, you will have parallel component. So this is your parallel component. And in this case, you will also have a speed is increasing along a curved path. So this means you will also have this component. So you will have both component of acceleration. You will have this component of acceleration, and you will also have this component of acceleration. And if you take sum of these two, you will get the resultant. So resultant will be in this direction. So your resultant will come in this direction. The same thing is shown here. I can show this like this. So you will have something like this. So this is your parallel component of acceleration, and this is your perpendicular component of acceleration, and if you sum, this is your total acceleration. So this is your total acceleration. So in this case, you can see acceleration is ahead of this normal vector. So this is your normal vector. So this is your normal, and then your total acceleration is somewhere here. So you can say acceleration points ahead of the normal. So when a speed is increasing along the curved path, the total acceleration is ahead of the normal vector or normal, I can say. So A points ahead of the normal to the path or normal to the velocity vector. And third situation, you can answer yourself. What will happen when the speed is decreasing along the curved path? So you have to answer yourself, what will happen if a speed is decreasing? In the previous case, the speed was increasing. Now the speed is decreasing. What will happen? So speed is decreasing. This means you will have a tangential acceleration, but that tangential acceleration will be in this direction. And you will have a normal acceleration because direction is also changing. So you will have a normal acceleration, and that will point in this direction. So this is the normal acceleration, and this is the tangential acceleration. Why the tangential acceleration is in the opposite direction? Because there is a decrease in the speed. So increase in the speed, this side, decrease in the speed, this side, because the direction of a speed is in this direction. So now if I take the resultant of this vector, that is the perpendicular component, and this is parallel component, and if I take resultant of this two, I will get this vector, that is acceleration vector. Now see, this acceleration is behind the normal. So normal is here and this acceleration is here. So in this case, I can say acceleration points behind the normal. So if your speed is decreasing with time, acceleration vector is behind the normal vector or normal perpendicular to the velocity, that is the normal to the velocity or normal to the path. So I can say A points behind the normal to the path. So we illustrated how you can basically use the idea of tangential component of acceleration and normal component of acceleration to analyze motion on a curved path. In summary, I can say if you have only tangential component, this means object is moving in a straight line. If you only have perpendicular component, object is moving in a circle. And when you have both component, object is moving on a curved path, increasing the speed, and this also has change in direction of the acceleration. Now we will illustrate this using an example. So this example says, so we have a particle, and this particle has two acceleration component. Initially the total acceleration is given. This is the total acceleration of this particle. and this is the direction of velocity. So I know the direction of velocity of this object. So this object is at certain point of time, this object is moving in this direction. We have to calculate the component of acceleration along the direction of velocity and perpendicular to the direction of velocity, and the acceleration is given. This is 1 meter per second square. So magnitude of acceleration is given, that is 1 meter per second square, and I have to calculate what is the parallel component and what is the perpendicular component. So this is your acceleration, and this is your parallel component, and this is your perpendicular component, and this angle is theta. So if this angle is theta, so I can use this right angle triangle and I can calculate this one. So this angle is theta, and that theta is 30 degree in this case. So I can write cos theta is equals to A parallel divided by A, and I am writing in terms of magnitude. So A parallel is nothing but A cos theta. A is given, that is 1 meter per second square, and this cos theta is cos 30 degree, and cos 30 degree is nothing but root 3 by 2. So this is root 3 by 2 meter per second square. So this is A parallel acceleration. Similarly, I can write A perpendicular, this will be A sin theta, and theta is equals to 30 degrees. So I can write 1 meter per second square times sin 30 is nothing but 1 by 2. So I will have 1 by 2 meter per second square is the acceleration in this case. So we calculated perpendicular component, and this is the parallel component. So in this video we learned how to use a different set of decomposition of acceleration. Generally we use Cartesian coordinate, but when you have an object that is moving on a curved path, we try to use parallel to the velocity and perpendicular to the velocity. So we decompose the acceleration parallel to the velocity and perpendicular to the velocity, and then we analyze the motion. This is particularly important when we will go to the circular motion chapter. In that case, velocity magnitude is constant, the speed is constant, the speed is not changing, only the direction is changing. This means perpendicular component of acceleration is only changing, the normal to the path is only changing, there is no change in the tangential acceleration. So we'll come to this again in the circular motion chapter. For the time being, thank you, and I hope you have enjoyed this video and you will share with your friends. See you in the next video. Bye.